Hello? Do you know an interesting application of the notion of the slope of a tangent line to an implicit curve and of implicit differentiation? Let's solve the following optimization problem using GeoGebra. Let us find the dimensions of the cylinder with the largest volume that can be inscribed in a right cone of radius 2 and height 4. Let us also determine said maximum volume. Here's the diagram. A cylinder inscribed in a cone. Drag point A along the cone's generatrix. We see that several cylinders are formed with different radii, heights, and volumes. When the radius is 0, the height is 4 and the volume is 0. When the radius is 2, the height is 0 and the volume is also 0. So there must be a single cylinder with the largest volume. Variable magnitudes. These are the radius denoted by x, the height denoted by UAI, and the volume of the cylinder denoted by V with their domains indicated. By dragging point A along the generatrix of the cone, we see that pairs of similar triangles are always formed. Thus, the radius x and the height UAI must satisfy a proportion of similar triangles. This proportion is the condition of the problem. We construct the proportion of similar triangles. It is the implicit equation of the straight line, whose graph in the first quadrant is the dotted segment. The function to be maximized. This is the volume of the inscribed cylinder. The position of point A on the cone's generatrix determines the volume of the cylinder. For a given volume, we have the implicit curve in the first quadrant. By dragging point A, we notice that when the implicit volume curve tends to be tangent to the dotted segment of the condition, the volume tends to reach its maximum value. We intuit that when the cylinder's volume reaches its maximum value, the implicit curves of the condition and the function to be optimized must be tangent. They must share the same tangent line. That is, their implicit derivatives with respect to x must be equal at that point. Let's set u as a constant and equal to the maximum volume, the volume we wish to determine. Let's calculate the implicit derivatives in this equation and in the condition equation and equate them, from which we obtain the equation of the line UAI equals x. The point of intersection of this line with the condition line provides the point where the maximum volume is reached. The condition and the function are tangent at this point. So we see that point D gives the radius and height of the cylinder with the largest volume. The maximum volume is as indicated. The solution to this optimization problem illustrates an important application of the notion of a tangent line to implicit curves and of implicit differentiation. It demonstrates an alternative to the traditional one-variable method for solving elementary optimization problems. It also demonstrates the use of GeoGebra's current dynamic mathematics technology for understanding such problems.